Hello everyone, welcome back to alkaline hydroxide 784, and today in the chemistry series we'll be looking at carbonyl compounds. And they consist of the aldehydes and the ketones. So as usual, you'll be accompanied by a lot of background noise and you'll be looking at the learning outcomes that's seriously okay, sorry. We'll be looking at the learning outcomes. So the first one is describing the formation of aldehydes and ketones from and their reduction to primary and secondary alcohols respectively. So we already might have seen how they are formed in a way, and to form them usually will oxidize the primary and secondary alcohols as we have seen last time. You use KMNO4 or dichromate. We can use either of those. Of course, it depends on what exactly you intend to do with the alcohol. So or what kind of alcohol it is. If it's a primary alcohol and you want to make it an aldehyde, you can use KMNO4 because it'll just become carboxylic acid. So yeah, you have to use potassium dichromate and immediately titrate it out. And for secondary alcohols, you can just use KMNO4 because you just get a ketone. It doesn't matter whether you use KMNO4 or K2Cr2O7. I think that's why I just prefer saying dichromate. It's harder to say the number. Okay, so yeah, that's how you form aldehydes and ketones from alcohols. And if you want to go the other way around, which is to reduce them, you would use LiAlH4, which is lithium aluminium hydride, or you could use NaBH4, which is sodium borohydrate, borotetrahydrate. Okay, I don't really remember how exactly to say that, but okay, anyways. And then you can actually reduce them back to primary and secondary alcohols respectively. Okay, so the next learning outcome is, oh yeah, as usual, if there's any additional conditions or more specific conditions, I'll just write it down on the paper. Whatever I say may not be entirely 100% correct, but usually I'll just try to avoid saying it because I don't want to end up saying the wrong conditions. So the next learning outcome is to describe the mechanism of the nucleophilic addition reaction of hydrogen cyanide with aldehydes and ketones. So hydrogen cyanide is basically the HCN, where the C and N have a triple bond. And the nucleophile here is the C triple bond N. Yeah, and the C is the one that ends up attaching to the like either aldehyde or the ketone. So you're adding this over the C double bond O bond, and basically the H will attach to one end and the CN will attach to the other end. So what happens is, first of all, if you need a little bit of NaCN or something that provides a little bit of CN anions in order to start the reaction. So you either use sodium cyanide or sodium hydroxide, which will hydrolyze the HCN a bit and create some cyanide ions. So these ions are then the nucleophile, and they will attack the C because the C in the C double bond O bond, like the C double bond O, the C is actually partially positive, and it will attract the cyanide anion to actually come and attack it. And because of that, the double bond is forced to break, so the electrons will go to the O and the O becomes negative. And so now you have this situation where the C has this CN attached to it, and there's an O with a negative anion, like negative charge to it. So this negatively charged O will then attract a H from another HCN molecule, and that will then break the H off of that HCN, and you get a new CN minus. And of course, then you would need to remove the OH, right? So if you want to remove the OH, you then need to get another wait, you need to, oh yeah, that's it. Actually, that's how it works. That's basically the nucleophilic addition. So the CN adds the C and the H adds to the O. So you will get a kind of like an alcohol, but at the same time you have like a nitrile kind of thing. Yeah, that's basically what happens. And if you reduce that thing, you get a CH3NH2. So yeah, that's, in order to reduce it, you need LiAlH4. So yeah, that's basically that. And then yeah, that's what happens when you add hydrogen cyanide. If it's like aldehyde versus ketone, the final primary versus secondary thing will kind of affect what exactly it does in the end. Okay, so the next learning outcome is to explain the differences in reactivity between carbonyl compounds and alkenes towards nucleophilic reagents such as lithium aluminum hydride and hydrogen cyanide. Okay, so the difference between carbonyl and alkene is that carbonyl has a polar double bond kind of thing, while alkenes are just C double bond C, nothing exciting there. So therefore the carbonyl compounds will have a more polar bond, and it'll be more reactive because the C will be more positive and the O will be more negative compared to just two like C's attached together with a double bond. And yeah, it will be more attractive to nucleophiles, especially the carbon part of it. And that means that lithium aluminum hydride can, will react more favorably with carbonyl versus alkenes. But if you want to be even more obvious, right, if you use a weaker reducing agent like NaBH4, it will react with aldehydes, but like it will react with the carbonyl compound, but it will not react with alkenes. But lithium aluminum hydride kind of reacts with mostly a lot of things. Yeah, so I guess it will just be less reactive on an alkene versus a carbonyl in a sense. And for hydrogen cyanide as well, you would need harsher conditions to get it to work in an alkene compared to a carbonyl compound. Yeah, so that's how it works, as we've seen. Like, okay, actually I'm not sure if hydrogen cyanide really reacts with alkene. I guess it probably does. Okay, anyways, so the next one is describing the use of 2,4-dinitro phenylhydrazine to detect the presence of carbonyl compounds. Okay, so there's a reason why they abbreviate this to 2,4-DNPH. So I'll kind of just show you how to draw this particular compound. So you start with a phenol, which is a benzene with an OH group on it, and then you look at the 2,4. So you draw two nitro groups, 2 and 4, and then after that you know that this has it is hydrazine, so that will have the N2H4 group, and instead of OH, that is what will be there. So wait, no, is it? Okay, I'll just draw it properly and you get the idea what's going on there. So the phenol is attached to the hydrazine, that's the logic. So the yeah, like instead of OH, it is like O will be attached to the N directly and you'll get a 2,4-DNPH. Okay, so what this does is this happily will react with carbonyl compounds because of that wonderful O double bond. So actually the OH on the phenol doesn't react with this. It's more like this reacts with the O, like the double bonded O on the carbonyl compound. So it's pretty nice. It is actually quite fast, and it will start, it will just create like this precipitate and you can easily find it. Okay, so the next learning outcome is to describe the nature of an unknown carbonyl compound from the results of simple test. So we just need to decide whether it's aldehyde or a ketone. So like there are two different tests which will help you to somewhat distinguish between the two, apart from some exceptions. So if you use the Felling's reagent or Tollens reagent. So Felling's reagent is the one with copper in it. So if it's aldehyde, it'll turn red. If it's a ketone, for the most part, it will just remain blue. As for Tollens, if it's aldehyde, you get the silver mirror, which is pretty nice to observe, I guess. If it's a ketone, you will not get any silver mirror. Okay, so then the next way to test is using the ease of oxidation. So let's say you use I don't know, dichromate in the sense, and we already have the aldehyde and the ketone, kind of. So if you try to oxidize it further, the dichromate will then only change color when you have the aldehyde, because that's the only one that will actually oxidize further, not really the ketone. So for dichromate, you get the orange to green. Yeah, I think it's orange to green, it's not the other way around, right? Okay, orange to green. And if you use KMNO4, it's the purple to colorless. Okay. Yeah, that's pretty much what you can do. I mean, yeah, the last thing that you can probably do is to just find the aldehyde group, which is, this is the last learning outcome. Detect the presence of a CH3CO group in a carbonyl compound from its reaction with alkaline aqueous iodine to form triiodomethane. I believe we have looked at this last time, although I didn't really state, I just briefly showed that it works with these particular things as well. So if the carbonyl compound with the CH3C double bond O, so this is actually kind of like a ketone, it's not really an aldehyde, but the C double bond O is in the second carbon, if you think about it that way. You will then get this whole reaction with iodine to get your triiodomethane, which is that yellow oily substance that we saw last time. So I don't think I really need to cover this in greater detail. Can watch the previous episode to find more about that. Okay, so I think we are kind of done. I hope I had enough time to write. If I didn't, I should probably just go and be showing you all the stuff that I didn't show you earlier. But I think this shouldn't be too problematic. And yeah, that's about it. If you found this video useful, please press the like button and subscribe. And with that, I would like to say thank you and bye.